Right now, as you sit and watch this video, you're being held in place by something science cannot see, cannot touch, and cannot fully explain. It is not a theory from a science fiction novel. It is not a guess. It is the leading explanation for why galaxies do not tear themselves apart, why the universe looks the way it does, and why everything you can see, every star, every planet, every human being who has ever lived, makes up less than 5% of everything that exists. The rest is dark. The rest is silent. And tonight, we are going to explain what scientists actually know about it, what they still do not know, and why some of the smartest people on the planet believe we are on the edge of one of the greatest discoveries in the history of physics. My name does not matter for the next hour. What matters is that you stay with me, because by the end of this video, you will understand the universe in a way most people never will. Let us start with a simple question. If you spin a wheel fast enough, what happens to something sitting on the edge of it? It flies off, unless something is holding it there. Gravity works the same way across galaxies. Stars orbit the center of a galaxy the same way planets orbit a sun, and the speed at which they should be moving can be calculated using nothing more than the mass we can see through a telescope. In the 1970s, an astronomer named Vera Rubin decided to actually measure how fast stars at the edges of galaxies were moving. According to everything we knew about physics at the time, stars far from the galactic center should move slower than stars close to it, the same way Neptune moves slower around the sun than Mercury does. But that is not what she found. The stars at the edges of galaxies were moving just as fast, sometimes faster, than stars near the center. By every law of gravity we understood, this should have been impossible. Those outer stars should have been flung off into deep space, scattered like water off a spinning bicycle wheel. Something invisible had to be holding them in place. Something with enormous mass, wrapped around the galaxy like a cocoon, providing gravity we could not see but could absolutely measure through its effects. This was not the first hint of the mystery. Decades earlier, in the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He measured how fast individual galaxies within the cluster were moving relative to each other, and using the visible mass of those galaxies, calculated how much gravity should be holding the cluster together. The number did not add up, not by a small margin but by a factor of hundreds. The galaxies were moving so fast that the visible matter alone could never have kept the cluster gravitationally bound. Zwicky called this missing mass Dunkelmaterei, dark matter, and for decades, almost nobody took him seriously. It took nearly 40 years and Vera Rubin's meticulous measurements of galaxy rotation curves for the scientific community to accept that something was deeply wrong with our understanding of the universe. And once they accepted it, the evidence began piling up from every direction imaginable. Let us talk about gravitational lensing, because this is where dark matter stops being a mathematical inconvenience and starts becoming something you can almost see with your own eyes. Albert Einstein predicted that massive objects bend the fabric of space itself, and when light from a distant galaxy passes near a massive object, that light bends around it, like water flowing around a rock in a stream. This bending creates a lens effect, and by studying how light warps as it passes through clusters of galaxies, astronomers can map out exactly where mass is concentrated in space, whether or not that mass emits any light at all. When scientists pointed the Hubble Space Telescope at massive galaxy clusters and mapped the gravitational lensing effect, they found something remarkable. The mass distorting the light extended far beyond the visible galaxies, in some cases stretching out into vast, ghostly halos with almost no visible matter inside them at all. It was as if giant, invisible mountains of mass were sitting in space, warping the light of everything behind them, while remaining completely invisible themselves. The single most convincing piece of evidence came from something called the bullet cluster. And if you remember only one image from this entire video, let it be this one. The bullet cluster is actually two galaxy clusters that collided with each other millions of years ago. When galaxy clusters collide, something interesting happens. The stars themselves mostly pass through each other, because space between stars is so vast that direct collisions are extremely rare. But the hot gas clouds within each cluster, which make up most of the normal visible matter, slam into each other and slow down dramatically due to friction, like two clouds of smoke colliding and tangling together. Now here is where it gets fascinating. When astronomers used X-ray telescopes to map where the hot gas ended up after the collision, they found it clustered in the middle, exactly where you would expect two colliding gas clouds to end up. But when they used gravitational lensing to map where the actual mass was concentrated, the invisible mass had passed straight through the collision, completely separate from the visible gas, sitting on either side like two ghosts that had walked through each other unaffected. This was undeniable proof that whatever this invisible substance is, it does not interact with normal matter or with itself the way regular matter does. It only interacts through gravity. This single image, more than any equation, convinced the scientific world that dark matter was not a mathematical patch to fix a broken theory. It was real, physical, and separate from everything we can touch. So what exactly is this invisible substance? This is where things get genuinely uncertain, and where I want to be honest with you, because a lot of content online oversimplifies this or pretends we know more than we do. The leading candidate for decades has been something called WIMPs, weakly interacting massive particles. The theory suggests that dark matter is made of particles that have mass, and therefore exert gravity, but interact so weakly with normal matter, and with light that they pass through entire planets without so much as a flicker of interaction. In fact, right now, trillions of these hypothetical particles could be passing through your body every single second, and you would never feel a thing, because they simply do not interact with the atoms that make up your skin, your bones, or your blood. To hunt for WIMPs, scientists have built some of the most sensitive detectors ever created by human beings, buried deep underground in old mines and tunnels, shielded from cosmic rays and background radiation that could interfere with the incredibly rare signal they are hopping to catch. Facilities like the Xenon experiment in Italy and the Luxi PLIN experiment in South Dakota use massive tanks of liquid xenon, waiting patiently for the incredibly rare event of a dark matter particle colliding with a xenon atom and producing a tiny, detectable flash of light. Despite years of extremely sensitive searching, no confirmed WIMP has ever been detected. Each null result narrows the range of possibilities, but does not rule out the existence of dark matter itself. Because WIMPs have proven so elusive, another candidate has grown increasingly popular among physicists: the axion. Axions are theorized to be extraordinarily light particles, so light and so weakly interacting that detecting them requires entirely different experimental approaches, often involving powerful magnetic fields designed to convert a hypothetical axion into a detectable photon. Experiments like ADMX, the Axion Dark Matter Experiment, are essentially incredibly sensitive radios tuned to listen for a signal that may or may not exist, scanning across a vast range of possible frequencies in the hope of catching the faintest whisper of new physics. There is also a third, older idea, MACHOs, massive astrophysical compact halo objects. This theory proposed that dark matter might not be an exotic new particle at all, but simply ordinary matter that is too dim to see: black holes, neutron stars, brown dwarfs, and rogue planets drifting through the darkness of space. Astronomers tested this by watching for gravitational microlensing events, brief flickers of brightening starlight caused by a dark, massive object passing directly between us and a distant star. While some microlensing events have been detected, there are nowhere near enough of them to account for the total amount of dark matter required to explain galaxy rotation curves and gravitational lensing observations. MACHOs have largely been ruled out as the primary explanation, though the search for exotic astrophysical objects continues in parallel with particle physics research. Now, I want to introduce you to a genuinely fascinating alternative: because good science requires acknowledging where consensus is not absolute. A small but persistent group of physicists believe that dark matter may not exist as a physical substance at all. Instead, they argue that our understanding of gravity itself might be incomplete at galactic scales. This idea is called modified Newtonian dynamics, or MOND, and it proposes that Newton's laws of gravity behave slightly differently when gravitational acceleration becomes extremely weak, exactly the conditions found at the outer edges of galaxies. Under MOND, you would not need any invisible mass at all to explain galaxy rotation curves, because gravity itself would simply behave differently than Einstein and Newton predicted at those enormous distances. For years, MOND was able to explain galaxy rotation curves impressively well, in some cases even better than the standard dark matter model. But MOND has struggled badly to explain other pieces of evidence, particularly the bullet cluster, where the separation between visible mass and gravitational lensing is extremely difficult to explain through modified gravity alone. Most physicists today consider dark matter the far stronger explanation, though a small number of researchers continue refining modified gravity theories. And honest science requires us to acknowledge that the debate, while lopsided, is not entirely closed. Let us zoom out even further, because dark matter is not just about individual galaxies. It shaped the entire structure of the universe as we know it. Shortly after the Big Bang, the universe was an almost perfectly smooth soup of hot plasma. Almost perfectly smooth, but not quite. Tiny variations in density, smaller than 1 part in 100,000, existed in that early universe. Normal matter alone would not have had enough time or enough gravitational pull to grow those tiny variations into the galaxies, galaxy clusters, and cosmic superstructures we observe today. Not within the roughly 13.8 billion years the universe has existed. Dark matter, because it does not interact with light or radiation the way normal matter does, was able to begin clumping together under gravity almost immediately after the Big Bang, long before normal matter could cool down enough to do the same. Dark matter essentially built the scaffolding of the universe first, and normal matter, gas, dust, and eventually stars and galaxies, fell into the gravitational wells that dark matter had already carved out. This is confirmed beautifully by observations of the cosmic microwave background, the faint afterglow of the Big Bang itself, which was mapped in extraordinary detail by missions like the Planck satellite. The precise pattern of tiny temperature fluctuations in the cosmic microwave background matches almost perfectly with a universe that contains roughly 5 times more dark matter than normal matter, a figure remarkably consistent with what we observe today through completely independent methods, from galaxy rotation curves to gravitational lensing, to the large-scale distribution of galaxies across the observable universe. Speaking of large-scale structure, if you have ever seen a map of the universe showing the distribution of galaxies across space, you will notice something strange. Galaxies are not scattered randomly. They form a vast, web-like structure, filaments and clusters of galaxies stretching across billions of light years, separated by enormous, nearly empty voids. Scientists call this the cosmic web, and computer simulations that include dark matter reproduce this web-like structure with stunning accuracy. Simulations that exclude dark matter simply cannot recreate the universe we actually observe. The filaments of the cosmic web are essentially traced by the gravitational skeleton of dark matter, with galaxies glowing like cities built along invisible highways. So where does this leave us? What do we actually know for certain, and what remains a mystery? We know, with overwhelming observational confidence, that something with mass exists in far greater quantities than the matter we can see, and that this something exerts gravity but does not interact with light, or with normal matter, or seemingly with itself, in any significant way beyond gravity. We know it makes up roughly 27% of the total energy content of the universe, dwarfing the roughly 5% made up by all the normal matter, atoms, stars, planets, and living things combined. The remaining 68%, for context, is an even stranger mystery called dark energy, the force believed to be driving the accelerating expansion of the universe itself. But that is a story for another video. What we do not know is the precise nature of dark matter's particle physics, assuming it is even made of particles at all in the traditional sense. Every major detection experiment has come back empty so far, not because the science is flawed, but because whatever dark matter is, it is proving to be extraordinarily difficult to catch directly. Some physicists have begun exploring more exotic possibilities, including primordial black holes formed in the earliest moments after the Big Bang, self-interacting dark matter that behaves differently than the simplest models predict, and even the possibility that dark matter is not one single substance at all, but a mixture of several different exotic components working together. There is something genuinely humbling about all of this. We have mapped the structure of galaxies billions of light years away. We have detected gravitational waves from black holes colliding more than 1 billion years ago. We have photographed the event horizon of a black hole itself. And yet, the substance that makes up the majority of all the matter in the universe remains completely invisible to us, detectable only through its gravitational shadow, like a ghost whose footprints we can see perfectly clearly while the ghost itself remains forever out of sight. Every galaxy you have ever seen in a photograph, every spiral arm, every glowing cluster of stars, is embedded inside a vast, invisible halo of dark matter, many times larger and more massive than the visible galaxy itself. Our own Milky Way is no exception. Scientists estimate that the dark matter halo surrounding our galaxy extends far beyond the visible disk of stars, potentially stretching hundreds of thousands of light years into the darkness, an invisible sphere of gravity holding our entire galaxy together, holding our solar system in its orbit around the galactic center, holding the very ground beneath your feet in its place within the cosmic structure of the universe. Think about that for a moment. As you go about your life, you are not just standing on a planet, orbiting a star, inside a galaxy. You are standing inside an invisible cathedral of gravity, built from something science has never directly touched, something that outweighs everything we can see by a factor of 5 to 1, silently shaping the structure of everything that exists. The hunt continues. Deep underground in laboratories shielded from cosmic radiation, scientists sit patiently beside massive tanks of liquid xenon, waiting for a single flash of light that might never come, or might come tomorrow, and change physics forever. In deserts and mountain ranges, radio telescopes scan the sky for axions. Particle accelerators smash protons together at nearly the speed of light, hopping to create dark matter particles in laboratory conditions and catch them in the act. And in the depths of space, telescopes continue mapping the gravitational fingerprints of dark matter across billions of galaxies, refining our picture of the invisible scaffolding that built the cosmos. We may be one experiment away from the answer. We may be decades away. But one thing is certain. The universe we can see with our eyes, the stars, the planets, the galaxies, is only a small, glowing fraction of a much larger, much darker reality. And somewhere out there, hidden in plain sight, is the answer to one of the greatest mysteries science has ever encountered. If this video helped you understand dark matter in a way you never had before, take a moment to subscribe, because we are exploring the deepest mysteries of the cosmos every single week, and this is only the beginning of the story. The universe is far stranger and far darker than most people ever realize. Stay curious, stay looking up, and I will see you in the next one.